Hello, this is a Curious Axolotl for the first ever video on this channel, and today we'll be deriving the barometric law. The barometric law is a formula that tells us how pressure or density, we'll be deriving pressure here, varies with altitude in the atmosphere. Now this derivation is easy given that you know where to start. Here's the equation itself, P of z, which is pressure in terms of height or altitude in this case, equals to base pressure, and here we have a value in the exponent, minus m, which is molar mass, g, gravity, over RT, natural gas constant, and temperature, multiplied by z, which is in our case height or altitude, since this is an equation used in atmospheric physics. And it is known as the barometric formula. Not barometric equation, not barometric whatever, the barometric formula. Now, if asked to derive this in, let's say, an exam, all you really got to memorize is the ideal gas law and the hydrostatic equation. Let's write those out. The ideal gas law is PV equals nRT. This we should know ever since 6th, 7th grade. The hydrostatic equation, on the other hand, you might not know unless you're into this field, or you might if your school was good enough. dP equals dz equals minus rho g. I'll rearrange this formula a bit to yield minus rho g. Taking the denominator to the other side, we need to multiply it by dz on both sides, and this dz cancels with the dz we multiply here, and here we would get the minus rho g multiplied by dz. Now, in order to solve for the barometric formula, which is pressure in terms of height, we need to separate out pressure. But we notice here that it's an infinitesimally small part of pressure, that's what dP means, and we need to integrate in order to get pressure out of this. In order to do so, we need something to integrate with, and we can't really work with this density unit here, so what we're going to do is we're going to separate out density rho in our ideal gas law, PV equals nRT. In order to do so, let's just do V to the other side and RT on the left-hand side. We get PRT equals N over V. I did the same procedures here. This is basic math. And from there, we have this expression. Now, unfortunately, N over V is not equivalent to density, rho. We know that rho is equivalent to mass over volume. Now, how do we get mass over volume from what we have here? We will notice that what we have here is pressure over the ideal gas constant multiplied by temperature T. On the other side, we have the number of moles divided by volume. Now, in order to change this into mass over volume, we simply need to multiply the numerator by molar mass, because we will remind ourselves that molar mass multiplied by the number of moles is equivalent to m. Doing this up here, we need to do it both sides. We get mp over rt equals mn over v, and that equals to m over v, and that equals to density rho. I hope I didn't lose anyone so far. So what we essentially did is we went from the ideal gas law to an expression for density rho. Now that we have an expression for density, we may do what we planned to, which is plug it into the hydrostatic equation, and what we get then is simply dP equals minus mp over rt, literally as it says here, multiplied by g multiplied by dz. Now, at this point is where things get interesting, and this is a technique that is taught in calculus. It's known as separation of variables. Separation of variables simply means taking all variables of one sort to one side and all variables of the other sort to the other side, so you may integrate. What we're going to be integrated with is given by what are the infinitesimally small parts, dP and dz. So we're going to integrate on this side in terms of p and on this side in terms of height or altitude. we notice straight away that we have no terms that correlate with z. There's no z terms anywhere here, and so we assume that nothing actually varies with altitude except pressure, which of course we'll derive later. And on the other side, we do have a p-value in the right-hand side, so we take that to the left-hand side by dividing both sides by p. This p will cancel by the divisor or divisor, or whatever you call it, and this p will come down as minus p dp equals minus m. Then the p here is gone. We'll substitute the g. We're going to kind of combine our constants here. Mg rt, and that is, of course, all multiplied by dz. Now, the steps to separation of variables, of course, is separate the variables and then integrate. We will now integrate both sides, because separation of variables does require you to integrate both sides. Conveniently, notice that I've already taken out mg rt. We've taken the constants out, so we can integrate just dz alone, because there's no z-related term other than that. Here we do have 1 over p, and that's going to stay inside the integral because it is a term that is p-related. So our integration will look something like this. Our integration limits will be p of z, pressure in terms of height, to our base p value. And then on this side, our integration limits will be z simply and z base height. Base height will assume to be 0 meters, so we might as well not even include this. I will continue on to the next step with this in mind and then show you why this is unnecessary to include. So then what we end up having is we integrate both sides. Here it's simple, here it's, well, so simple. And we know what we should know and what we should remind ourselves is that 1 over p dp, disregarding the fact that it's pressure or any other variables, it'd be the same for 1 over x dx, we would have ln p. We, of course, to both of our limits, p of z and p naught. On the other side, our constant stays the same. The constant never changes. That's quite self-explanatory because we didn't actually do anything to it. It stayed outside the integral, and it will stay outside the integral now. This does evaluate simply to z, to, of course, both our integration limits, z and z0, which we know is 0 meters, as we stated before. And now, plugging in our integration limits, we get okay, and this is where we get rid of z0, because we know that it is equivalent to 0 meters, and as it's equivalent to 0 meters, we're going to eliminate it, because this is essentially z minus 0, so that gets crossed out there. Let's follow on to fill up this empty space on this page so that we don't waste paper, and let's remind ourselves that there's a log property that tells us ln, let's say, not necessarily p of z, but ln x minus ln y would be equivalent to ln x over y. And by the same principle, we can write that, which is equivalent to minus mgrt, well, there's a minus there, multiplied by z, our height. This constant we're going to pretty much keep throughout the entire derivation. Just be reminded that it's equivalent to minus molar mass multiplied by gravity, so 9.81 meters per second squared, over universal gas constant multiplied by temperature. But that's all you need to know for now. So from here, what we can do is we can raise both sides to the e, so we can cancel out the natural logarithm here, and doing so gives us for future reference, I'm going to use this shorthand that we used in the beginning, which simply means exp. That is equivalent to e to the power of, but when you're dealing with big exponents such as these and you don't want to write them small, you put exp and then whatever's in the brackets is e to the raised to that power. Let me adjust the page so everybody can see better. And from here, we know that e cancels with the natural logarithm, and we get an expression such as this one. We take the p naught to the other side. In other words, we multiply both sides by p naught. This will cancel, this will stay. And there you have it, ladies and gentlemen. This is pressure in terms of height. We say pressure in terms of height is basically a function f of x because you have this expression in terms of x. So once again, we have pressure in terms of height is equivalent to base pressure. So whatever the pressure is of the surface, in atmospheric physics, that would be standard pressure, which would be equivalent to 1013 HPA or 1000, correct me if I'm wrong, but that should be 1013 multiplied by 100 Pascal. We multiply that by an exponent, or rather e to the power of minus mg over RT multiplied by z. Once again, m is molar mass, g is gravitational acceleration. This will be rather constant. M will depend on whatever molecular species you're looking for. Oftentimes, you're just going to look for air, and in which case you calculate the molar mass of air. And that is over universal gas constant. That will stay the same always. Temperature will vary, and oftentimes in equations, or in problems rather, you're going to get a given temperature, and you need to calculate the pressure at a given temperature and then the given height. These two values will vary. And there you have it. This is the barometric law, assuming the temperature is constant with altitude. And so as to give a sort of a cliffhanger to the next episode, we are going to take this term right here without the minus sign, mg over RT, and we're going to say that is equal to 1 over h. Then h is equivalent to RT over mg. And h is a very important quantity in atmospheric sciences. It's known as the scale height, and just from this formulation alone, it should tell you that h is equivalent to the height it takes for pressure, for example, to fall down to a factor of e. And that's it. Thank you very much for seeing the very first video posted on this channel. If this gets trending, if this gets good reviews, whatever, then this channel is going to continue. And if there's any particular physics derivation, this could be physics. I don't delve into pure math, but anything related to physics or even chemistry, I can derive. Post in the comment section below, like, and possibly subscribe if you like the stuff on this channel. Thank you very much.